Okay, thank you very much, and I'd also like to thank the organisers for inviting me to give a talk here. So this is recursive, predictive, non-parametric. Everything would be quite straightforward in the predictive setting. And this is joint work with Richard Hahn, who's at Chicago, and Ryan Martin, who currently is at UIC, Illinois, but is moving to North Carolina State University in the fall. Okay, so Bayesians probably are aware that prediction is one of the key aspects of inference, fundamental to Bayes. One recent idea that people want to think about is how to do it fast. So you can do it very slowly. For example, if you take one of the well-known mixture models, Bayesian non-parametric mixture models, you can have it going very slow. You get an observation, you update the posterior, and then you have to, well, you can use the MCMC to get a predictive at the same time. But every time you get a new observation, you have to redo the posterior and get out the next predictive. There is an algorithm by Newton which actually takes a current posterior, takes a new observation, and then actually has a fast approach to updating the posterior. It does involve an integral in actually updating the posterior, and then you've got another integral to get the predictive. Okay, so it's fast, but technically it has some aspects to it which can still slow it down. So what I'm going to try and do is to actually try and get a recursive predictive setup of this type here. So the idea is that I've got my current predictive, I see my new observation xn+1, and then I try and go direct just using those two to get to the next predictive fn+1. And obviously that new predictive is going to depend on the all the sample x1 to xn. So this is for IID. So I'm going to only be doing this for IID observations. And from being a Bayesian from beginning, PhD, I've always believed that Bayes and IID don't go together. The idea is that you assume your X's observations are exchangeable, and the implied assumption is that they're dependent. Okay, you have a joint density on this exchangeable set of observations, and that implies some sort of dependence. So I've always thought that Bayes and IID don't quite go together. So that's more acute. That problem becomes more acute when you do asymptotics. So there's two styles. There's the Doob style. So the Doob style is one that was around in the 50s. But the assumption of Doob is that that comes from here. Okay? So to me that just seems a little bit unrealistic, that actually the predictive I've got, in order to meet the Doob criterion, you assume that this comes from here, which is a bit of a strong assumption. The assumption that the observations are IID, if you study Bayesian asymptotics from that point of view, you become labeled as a frequentist. So it's labeled as a frequentist study of a Bayesian model. So I've always been trying to find an answer to this. I haven't got one. So if you do Bayesian study of if you do an asymptotic study of a Bayesian model assuming IID, you're a frequentist. But the alternative, i.e. the Bayesian way, has to make this sort of very strong assumption that this is coming from here. Okay? Okay, so to motivate what I'm doing, I'm just going to try and re-look at Bayesian prediction. The maths is the same, but it's just looking at things from a slightly different perspective, which sort of allows you to think about how to look at Bayes, and then go on to look at how to do some fast Bayesian prediction. Okay, so Doob would assume that x1 does come from here. Okay, so I think we can all agree that that's probably unlikely. based on your first predictive. So if I see x1, I assert it provides information about the density from which it's coming from, and therefore it's in my best interest to predict x2 coming from somewhere different. Okay? So I've acknowledged that this is wrong. I see x1 coming from the density I'm trying to estimate, so it makes sense to change it. Okay? Just to make the density functionally dependent on the x1. Okay? So that's a very simple idea, just changing the first predictive in light of the observation I've got. I can carry on that argument ad infinitum. So if I've seen x1, x2, I make my predictive for x3 functionally dependent on those. It makes no assumption that x2, x3 depend on x1. It only says that the density from which they come depends on the x's, previous x's, for a very good reason. Okay? Because I'm trying to learn about the density from which they're coming. If I then put all those together, I do end up with a joint model predictive for the first n observations. And if I believe that these x's are IID, I certainly believe that that density should be symmetric. Okay? So however complicated this might look, what I'm going to try and do is make sure that this is a symmetric in the arguments x1 to xn, okay? For the reason that I believe that these are IID and therefore this should be symmetric. Okay. Okay, so that's what I've just said. And Dave Finetti's talked about exchangeability, but Hewitt and Savage actually talked about symmetry. They talked about the symmetry of the joint density of x1 to xn. And that's basically the argument, that if I have these symmetric densities, then I must have my prediction looking like this. Okay? That's the only option. So it's not a matter of starting with the x's being exchangeable, it's just this desire to keep changing my prediction every time I see something new. And this obviously is just the usual Bayesian posterior distribution, okay, based upon some prior PIDF. Okay, so that's the predictive. And there's something very nice about it being some average over some measures, the probability measure here. However, if I use this model here, and I have this as something complicated, so in Bayes nonparametrics it's something that's gets quite complicated. The complication is due to this coherence, this idea that these predictives have to interact with each other in a particular way, which is part of the Bayesian framework. This is what comes out as a necessity of being using a Bayesian model. So the claim here is that that may be a nice coherent equation to have. However, it's going to end up causing trouble in computing this thing. And the question is whether that contributes anything to accuracy. So the question is, does that actually contribute anything to me being able to predict accurately? Or is it just something that gets in the way and causes this thing to be quite cumbersome? Particularly when you come to these Bayesian nonparametric models. Okay, so the idea is that, unfortunately, as this is a Bayesian conference, and that is probably one of the key ideas or aspects of Bayesian inference, the idea is that in nonparametric models, it's too cumbersome, it creates problems, it forces things to be slow, and it doesn't contribute to doing anything better than you'd be able to do without it. So that's the idea. So to get something fast and accurate, the idea is to dispense with this thing here. Okay, so let's just have a look at what the predictive update actually looks like. So remember, we're trying to get something looking like this. The idea is to try and get something like this, to understand it, and then to implement it. So we've already agreed that actually you probably have to go through the posterior. The posterior gets a bit messy. So that's the posterior, sorry, the predictive. I've written it in slightly a different way so that actually the posterior based on n+1 has been written with n and then just brought out the n+1 observation. I've then just basically multiplied and divided by the current predictive at the same value x. So it's starting to look like the equation that we actually want to end up with. Nothing's really been solved here because this is still a complicated expression. So for example, again, if this prior is based on the mixture of Dirichlet process, this is something that's pretty much incomputable directly. So that's where the MCMC has to come in. So this is the term, this is okay, this is okay, this is a mess. This term is this. And for some reason, look as hard as you can find, that is a copula. Yet its representation as a copula in Bayesian inference has not actually been utilized. So for some copula, it may be complicated, it may be messy. In parametric models, it's actually simple. You can write that term as a copula based on n, with the current distribution functions of the prediction sitting in here. Okay? So it becomes a very simple, elegant looking thing. The only complexity left is this copula, the form of actually working out what the copula is. It's no surprises that that complexity is still attributable to this formal notion of coherence here. So the complexity of that copula is due to that coherence equation. If that coherence equation can be dispensed with, then it leaves room for this copula actually starting to become something a little bit more simple and to be able to be computed directly. And actually, it doesn't matter what Bayesian model you're working with, there's always a copula lurking behind it, a sequence of copulas which depend on n. Okay. So this is the direct update. And again, as I say, I haven't made much progress yet because this thing is still going to be complicated. Okay. So this is just a very simple example as to what kind of things happen when you look at it from a copula point of view. So this is a very simple model, exponential, exponential, and very simple derivation. You can show that the copula model that lurks behind this Bayesian model is the Clayton copula. And the parameter is 1 over n. You can actually then start looking at more types of simple model based on exponential family, and you can derive exactly what the copulas are again. So it's a nice representation. It's nice because you can go direct from the copula, multiply by the current predictive, and get the next predictive from there. It's no surprise that the normal model gives you a normal copula, and the parameter of the normal copula is 1 over tau plus n, where tau is the it's not the variance, it's the precision, and n is the sample size. Okay. So as I said, when you have very simple models, the copulas become very simple. The coherence equation doesn't actually make anything messy in that particular case. For the next example, things don't get messy, but they give an indication of what life might be like when you try and be non-parametric with this. So the Dirichlet distribution is a very good example of for looking at in order to get an idea of what a non-parametric version of, say, the normal model might end up looking like. The upshot, and it's not difficult to go through all the details, is that you get a mixture. And the key here is, so this is for one update, so I have to stress, this is for one update starting from the prior and going to from the first predictive to the second one. So this is the copula. It's based on the independence copula, so it's a weighted mixture of the independence copula and the Frechet-Höfting copula. So what we can take away from this is that something non-parametric should have a mixture representation. On one side, you should have something looking like the independence copula. So if you remember from here, we want this to converge to the independence copula, right? That's where we want things to head. So this is sitting here. This is another part which will be dependent on the actual model you're looking at, and they have this weighting here. So if we were to keep applying this, the idea is that this hopefully would end up going to 1, and we end up at the independence copula for n large. Okay, so this is now getting to the matter of the non-parametric model. So as I said at the outset, a common Bayesian non-parametric model is something like this. So you have a kernel, usually the normal distribution indexed by a parameter, and then a large class of prior distribution mixing over that parameter. Necessarily discrete. If it's continuous, you haven't solved the problem because you're trying to model a continuous thing here. So out of necessity, this must be discrete. And the one that everybody started with, although there's huge quantities of these type things floating around these days, the starting one was the Dirichlet process. So this is a discrete, generates discrete P's. I haven't got how it works, but basically, if I keep taking samples from here, I can take weights, random weights, which are based upon this parameter here, and then I just connect up those weights with all of these set of random locations which are coming IID from here. So what's crucial to us to try and get an understanding of what's going on is to look at the first update from F naught x to this F1x. And that is not difficult to find. I can find exactly what this copula is. We're expecting a mixture because we know we have some sort of non-parametric thing going on here. And again, the mixture is a combination of the independence copula, and this is a Gaussian copula. Again, no surprises that it will be a Gaussian copula if I have these as a family of Gaussian distributions. So the first update is this. As I collect more and more data, this copula that I would need to go from n to n plus 1 becomes more and more complicated. It becomes so complicated that actually you're left with just doing MCMC to actually compute it and then get the predictive. So the idea here, obviously that also is in keeping with this coherence requirement of the integrating of the n plus 1 predictive down to the n predictive. So the idea here is that this update, the first one, is good. It must be good. It's taking the first predictive F0 to F1 with an observation. So the underlying assumption is that that in itself must be a good update. And it's this Gaussian copula with this mixture model. So as you saw with the Gaussian copula, I had the rho n. What's the aspect that makes this thing converge in the Gaussian copula when I just have one normal? It's the rho n. It's the rho n decaying to 0 at a rate 1 over n. So it wouldn't be a good idea to replicate that here and make this a Gaussian copula which depended on rho n, because it would only be this thing that changes and I would keep the alpha static. So instead of doing that, all you need to do is translate that decay that would be in the Gaussian copula into the mixture. And to replicate a sort of decaying idea to the independence copula by allowing this alpha to go to 0 at a particular speed. So the speed at which you send this thing to 0 is going to determine the accuracy. So basically what you're doing is taking the first update. The idea is that that's a good update. You end up with this mixture component and then putting all the burden of carrying this thing eventually to the correct density by just changing the weight in which you update that mixture. From one point of view, you could say that you'll just keep doing the Bayesian first update. You just keep replicating it, but you keep putting more and more weight on the independence copula rather than the Gaussian copula. Okay. So the claim is that that has no detriment to the overall accuracy of what you're doing. You're just eliminating a very annoying constraint which slows everything down but doesn't actually contribute to the overall accuracy of what you're doing. So as I said, this will then form the basis of the update. It does look a lot like the Newton's update where he would have these as the posterior distributions. The irony is that while the predictive you associate with integrals actually having to evaluate integrals, which certainly Newton's does, this has no integration whatsoever. So this is a remarkably trivial update to perform. I have these distributions. I just need to evaluate the Gaussian copula at a few points, take a grid of x's. I just need to work out what sequence alpha n guarantees this thing behaving in the right way. It's even more simple to look at it directly from a distribution function point of view, because then you're just taking distribution function to distribution function. And this is not the copula density, it's not the copula distribution, it's the one in between where you've either integrated one or differentiated the other to get this function here. So as that stands, that's an unbelievably trivial update to perform, and it's incredibly fast, very fast indeed. So these are not the actual pictures we have in the article. These are just things I knocked up myself, just using that algorithm on the distribution function. I just didn't do anything special at all. I literally just started it at the green. So the green is where it starts. I can't read. I think the true is red and the blue is where we end up after 1,000 observations. So it's something that works. It clearly works. I haven't mentioned the alpha n. Oh yes, so 1 over n is good enough for the convergence. Here are some others. This one probably didn't do as well, probably needs a few more. But again, you can see that it picks up the shape quite nicely, even from a very sort of smooth starting position. And here's another one. Again, so this is on 0 infinity. This is the starting point. And again, it ends up at the right place. So it's accurate, very accurate, and it's very fast. So we actually found out that we needed to do some slightly different asymptotics here. Because I'm not sure anyone had looked at, so if you look at Bayesian asymptotics, you have to go through the posterior first. You show that the posterior does the right thing, and then you show that the predictive does. So we had to show something like the predictive does something sensible from scratch. We don't have any priors or posteriors here. Okay, the only thing we start off with is the prior predictive. There is no posterior distribution here at all. So I just give an outline as to how the idea works, and I always get tripped up on this. The basic idea is that you can show that Fn converges to something, and the idea of showing it converges something is based on a Cauchy sequence. What you can then show is that the thing it converges to must solve this fixed point equation. So if my Fn goes to F, then the F must satisfy this condition here. Okay, so that's just a fixed point equation. And then lastly, you have to show that the only F that actually solves that is the true distribution from which you're actually generating your observations. So it's a very straightforward argument. There are some technical details that need to be filled in, but that's the basic outline. That you know your Fn converges to something, that something has to solve this, and the only thing that does solve this is the distribution generating your observations. If you're going to put some extra conditions on the true density, then you've got some stronger results, which is that your sequence of predictive densities converge in L1 also to the density that's generating the observations. So we have done some cases where we look at the densities, but predominantly just looking at the convergence of the distribution. The distribution is usually good enough because to predict, you just need the distribution. If you want predictive samples, you just need the distribution function. So as I said, it's remarkably fast. And that's suitable when you're looking at observations that arrive sequentially. So current work I'm currently undertaking is to look at this now from a sort of regression, more than one type of observation idea. So the idea here is that I'm actually wanting to predict from two or more distribution functions, and in some way I think that they're close to each other. So this is not saying that the observations from one sequence are dependent on the other. This is only saying that if I've got an observation from F1, somehow I think that that helps my knowledge about the density F2 and vice versa. So it's not saying that they're dependent on each other. It's just saying that I think I learn about one density by observing an observation from the other one. So the key to this is a joint density on, say, F1, F2. And then the key to that becomes I need to work out what these are. So just as I needed to work out what the predictive was for X2 given X1 from the same density, this now needs me to be able to write down what I think a predictive is for F2, given that I've seen an observation from X1. And that predictive is going to come from this joint. So how you construct that joint is everything. And this is actually a real challenging problem. So I could even draw for you two densities or distributions F1, F2, could show you what they actually look like, and then say, okay, can you now tell me what kind of a joint model you think you'd like here, that if you saw an observation from one of them, your predictive for the other one sort of makes sense. Even if you knew what they look like, it's a hard problem. So I suspect that there has to be some adaptation going on here, that as you learn more about what each of these two densities is, you try and use that information to improve what you would regard as these initial predictions. So what helps, actually, if you assume to get these two things, is to assume that they're based upon two mixing distributions with P1 and P2, and then actually try and get a joint P1 and P2. So this isn't going to be a regular joint distribution on P1 and P2. This has to be something quite well thought out as to how you actually believe these two things should actually, because they're everything. So these become everything now. Those are the things that are going to actually either work for you or not work for you. And so they have to be very carefully thought out. And at the moment, I don't think I or the colleague I'm working with really know or perfectly pinned down exactly what those should be. Okay, so to summarize, so I don't believe at all that there's any conflict between a Bayesian model and working with IID observations. And I certainly don't think that just because you look at the asymptotics of a Bayesian model under that assumption, you deserve to be called a frequentist, which is what happens. So the idea is that the Bayesian model just changes the prediction because you've seen things. It's just a functional dependence. The density depends on the past, not the next observation. So this is also the key. The key is how important is that to the Bayesian model? Is it essential? Is it disposable? What role does it play? Does it play any role in accuracy? Or does it actually take away from accuracy? Is it something that actually removes accuracy from the model itself? And the basic idea is to take the first update from a non-parametric model, which has this mixing parameter alpha. The idea is to repeat that update. That alpha controls how fast you go to the independence copula, just like any parametric model would do as well. The whole idea behind a parametric model and the copula is how quickly that parameter in the copula takes you to the independent copula. So the same idea is exactly here. That thing, the mixing parameter, tells you how quickly you go to the independence copula. The update being exactly the same as the first one. The simple idea is that that must be a good update. Okay, it's a Bayesian update. It's the first one. Doesn't make it probably any better or any worse than any of the other updates. But it's certainly something that you can actually keep replicating, change the alpha n, and you're guaranteed the accuracy very fast and without all the turmoil that's associated with the full posterior. Okay, that's the talk end. Thank you very much. Okay. For the bivariate problem? Yeah, so if, you mean if I, instead of having just x, I have a pair xy?
This is the previous slide. You see the prior that is a liberating ratio. Maybe one more. Yeah, this one.
Oh, this one? Yeah. So that just, no, that's not putting a joint on pairs of variables. That's putting a prior on one sequence, a prior on another sequence, but the underlying assumption is that I believe the distribution of those two sequences are close in such a way that I think if I see an observation from one sequence, I've learnt about the distribution of the other sequence. So it's not modeling a joint distribution of variables. It's that I really do think that, for example, males and females. So I see an observation from a male, And I think I've learned something about the distribution for females by observing that. And it's a question of how do I predict an observation for a female given that I've seen an observation from a male? And that's you'd model that with a joint pi P1, P2.
Popular representation.
You mind using the microphone?
Yeah. In a copular representation that you have, you've written it for x's which are real valued, but presumably there's an easy multivariate way of rewriting that. You've got writing in terms of a CDF.
Yes.
But is it? We can do that in a multivariate way as well. How does that all?
Yeah, so that can extend to multi. So for one sequence, I only need the bivariate copula because I'm only connecting up xn and xn plus x and xn plus 1. When you do have a bivariate sequence, so you've got, then it's more complicated. Yeah. It's harder to write down a copula for that. Yeah. But for the one sequence, it's remarkably simple.
Any more questions or comments? In that case, we'll finish there and let's